One of the greatest mysteries of chemistry would be cracked by this device. What is it? It's a cathode ray tube. You're probably watching this picture on a modern version of one of these. As the voltage is turned up, a strange glow fills the tube and casts a shadow at one end. Some kind of ray is shining down the tube. But this is not just a light beam, because the presence of a magnet causes it to bend and distort. By 1897, J.J. Thomson proved that this ray was a stream of fast, tiny charged particles, each with a weight less than 1,000th of the weight of a hydrogen atom. Tiny indeed. These were subatomic particles, particles of pure electricity. They called them electrons.
Electrons are the answer to the big question in chemistry, which of course is valency. Why does hydrogen only have a combining power of 1? Why is oxygen 2, nitrogen 3 and carbon 4? Why do the elements have all of these rules about them? The periodic table laid out the rules, but it didn't explain them. Electrons did, especially when they discovered that the electrons were the outer bits of atoms.
Electrons are like an atom's clothes. When atoms come together, it's the outer electrons that meet. Now, electrons are particles of electric charge. Of course, every atom has a nucleus of opposite electric charge to the electrons, so the picture is quite complicated. But as far as the chemistry is concerned, it's the electrons on the outside and how they interact when atoms come together that matters. Chemistry is completely down to electrons.
By 1924, it was clear that each type of atom had a characteristic number of electrons. Starting with hydrogen, which had but one electron, you could derive each element in the list by adding one more electron each time. Electrons formed orbital zones, creating shells or layers around the atom, and only certain strange and distinctive shapes were allowed. It was the electrons of the outer orbits which created the chemical rules. For example, when the outer orbits of a shell were fully loaded, that atom was stable and quite unreactive. The fully laden number was generally 8 electrons, a key number which had showed up on the periodic table and puzzled chemists for some 60 years. But elements without a perfect 8, and that was all the rest, showed considerable willingness to lose or gain or share electrons, thereby taking on a positive or negative electrical charge. Opposite charges attract, so an atom which has lost some electrons would bind to another with an excess of electrons. A compound would be created according to the strange but specific rules of quantum theory.
Electrons explained the mystery about benzene, for example. Remember how in the 1850s, Kekule worked out that benzene was a ring of 6 carbon atoms with floating double bonds. Why did this make benzene so unreactive? Electron theory showed that these so-called floating bonds would smear themselves out in a double donut shape around the entire ring, a very stable arrangement. Electrically, and therefore chemically, benzene is in a class of its own.
Electron theory explains, for example, why oil will not dissolve in water. Look at it, it just sits there. Because carbon atoms share their electrons equally between them, no one atom dominates the bonds between them. But in the case of water, H2O, the oxygen dominates the bond between the hydrogen, pulling the electrons toward itself. Thus, a molecule of water has a negative side near the oxygen and a positive side near the hydrogen. It has electrical polarity, and it can attract other polar compounds like sodium chloride, for instance, and dissolve them. But hydrocarbons, on the other hand, don't show any polarity. and don't respond to this electrical activity. Oil will not dissolve in water.
But when hydrogen in hydrocarbons is replaced by other elements, the story may be different. Other types of atoms may indeed introduce polarity, making the molecule soluble. Take soap. For thousands of years, people have made soap by reacting animal fat with wood ash. The sodium hydroxide from wood ash reacts with the triglyceride of the fat or oil to make soap. The sodium end of the molecule is polar, so it is attracted to water, while the organic end mixes with oil and dirt. So soap lifts dirt into water and it can be washed away. Atoms other than hydrogen attached to a hydrocarbon chain like this create lots of chemical variations.
Think of all the organic concoctions people have made for ages. Perfumes, wine, alcohol, drugs, paper, vinegar. They're just a few, for example. What about the ones we use directly, like milk, meat, fruit, vegetables, wood, wool? Traditionally, they're all derived from plants and animals, and that's what the word organic means, from life.
The hydrocarbons are in fact merely a starting point for a great variety of organic compounds, created by replacing some or all of the hydrogen atoms on the carbon chain. For example, take methane gas. When a chlorine atom is substituted for a hydrogen on the methane molecule, the new substance is called chloromethane. Like methane, it remains a colourless gas, but unlike odourless methane, it has a faint sweet smell, and instead of being harmless, it is moderately poisonous to breathe, creating dizziness and even convulsions. Replace 2 hydrogens with chlorines and you have dichloromethane, a volatile liquid used as an industrial solvent. Don't breathe the fumes. 3 hydrogens replaced and you have trichloromethane, better known as chloroform, a liquid whose fumes are a potent anaesthetic. They stopped using it in hospitals because they found out it caused damage to the liver, kidneys and heart. Tetrachloromethane, where all the hydrogens are now replaced by chlorine, is the toxic liquid commonly called carbon tetrachloride. It used to be dry cleaning fluid before they banned it.
This idea of replacing one or more of the hydrogen atoms on a carbon chain with other elements is referred to as a substitution reaction. There's a very nice story about how chemists woke up to this type of reaction after the Royal Ball in Paris in 1834. All of the aristocrats were sent into coughing fits after the candles were lit because they gave off a really acrid smell. Andre Dumas got the job of finding out what the hell was going on. He discovered that the candle maker had a batch of yellow wax that he wanted to turn white, so he heated it with chlorine gas to bleach the wax. In fact, some of the chlorine gas actually combined with the wax to produce a chloroalkane, and when it was burned, it gave off choking hydrogen chloride gas. So Andre Dumas experimented and came up with substitution theory.
Sometimes, like with chlorine, it's a 1-for-1 atom substitution. But more often than not, a hydrogen is replaced with a group of atoms. For instance, if a hydrogen is replaced with a hydroxyl, we get an alcohol. Now, there's a whole family of alcohols. Here's methanol. It has an OH group attached to 1 carbon. Here's ethanol, 2 carbons. Yes, this is booze. Here's propanol with 3 carbons. And here's butanol with 4 carbons, and so on. Now, I've already mentioned how an OH group in water is a polar combination. Well, here it makes the alcohol soluble in water. And I can demonstrate this by pouring a bit of methanol into water. Give it a bit of a swirl, and it should all dissolve. Of course, drinking alcohol is ethanol in water, and in vodka and whiskey, it's about 40% of its volume. True, as the carbon chain of the alcohols gets longer and longer, the solubility of these larger alcohols becomes less and less in water. But By and large, it's the OH group that determines the molecule's activity.
So in alcohols, the OH group is called the functional group. If you represented the hydrocarbon chain with the letter R, then the family formula for alcohols becomes ROH. And this is an easy way to designate family formulas for all organic substances. Let's take a brief look at the main families. Ethers are derived from the formula ROR. The best known of the ethers is diethyl ether, which was widely used for many years as a hospital anaesthetic. With amines, nitrogen gets into the act. RNH2 is the simplest arrangement, but it can be more complex. Amines are important industrially, and they are the base of proteins. Proteins include hair and muscle and bone. In other words, we ourselves are largely made of amine compounds. Then we have a superfamily built around functional groups which all contain an oxygen, double bonded to the last carbon on the chain. RC double bond oxygen H is the signature of the aldehydes. Perhaps the best known aldehyde is methanol. Dissolved in water, it's known as formalin and used as a preservative for specimens. And anybody who has painted cars knows lacquer thinner. This comes from the family of the ketones, which have the formula RC double bond oxygen R. Lacquer thinner is correctly called acetone. Orange juice. It contains citric acid, an example from another organic family, the carboxylic acids. Their formula is RC double bond oxygen OH. Carboxylic acids are quite weak, but they're common in nature. And when you smell the orange itself, you're smelling octyl ethanoate, which is from the family of esters. Their formula is RC double bond oxygen OR, and they usually have pleasant odours. Interestingly, animal and vegetable fats and oils are triple-ganged esters. They are complex triple-tailed molecules given the group name of triglycerides. As chemists worked through the identification of the functional groups of many natural compounds, they came to have increasing respect for nature's ability to make marvellous molecules. Consider the heme molecule, part of the hemoglobin in our blood. How complex is this? Bigger molecules exist, but they repeat more basic functional groups like bricks in a wall. Heme was finally deciphered in 1930. By then, the secrets of chemical bonding were well understood. But even in the last part of the 19th century, when the cathode ray tube was still a novelty, chemists were growing ambitious. Emboldened by their successes at deciphering what once seemed like a chaotic maze, they now set out to beat nature at her own game, to synthesise completely new substances. The stage was set for 20th century chemistry.